The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, great. Well, let's get going. Last time we ended up by discovering the electron. We discovered the fact that the atom was not the most basic constituent of matter. But in 1911, there was another discovery concerning the atom, and this is by Ernest Rutherford in England. And what Rutherford was interested in doing is studying the emission from the newly discovered radioactive elements, such as radium. And so he borrowed, or he got from Marie Curie, some radium bromide. All right? And radium bromide was known to emit some thing called alpha particles. And they didn't really know what these alpha particles were. Now, they did know that the alpha particles were heavy, they were charged, and that they were pretty energetic. That is what was known. Of course, today we know these alpha particles to be nothing other than helium with 2 electrons removed from the helium, helium double plus. All right, but Rutherford's in the lab, and he's got this radium bromide, alpha particles being emitted, and he's got some kind of detector out here to detect those alpha particles. And he measures a rate at which the alpha particles touch his detector. And it's about 132,000 alpha particles per minute. Okay, that's nice. But then what he does is that he takes a piece of gold foil, and he puts this gold foil in between the radium bromide emitter and the detector. And that gold foil is actually really very thin. It's 2 times 10 to the minus 5 inches, so 2 orders of magnitude thinner than the diameter of your hair. Right? So I often wondered how he handled that, but he did it. Right? So we put it in the middle here, and then went to count the count rate as a result of putting this foil there, and the count rate is, hey, 132,000 alpha particles per minute. Hey, didn't seem like that gold foil did anything. The alpha particles are just going right through to the detector. Hey, didn't even seem to matter that there was that gold foil. Hey, all right. So the postdoc that was working on it, Geiger of the Geiger counter, he was actually kind of disappointed. Gee, that's a boring experiment. But Geiger was even a little bit more unhappy because he had this undergraduate hanging around the lab. This undergraduate named Martzen. And Martzen was really enthusiastic about doing something in the lab. He really wanted to do something. And Geiger, what am I going to do with this kid? So Geiger goes to Rutherford. Look, this kid, he really wants to do something. What should I have him do? And Rutherford said, well, okay. What you should have him do is take this detector and have him build it so that it can be swung around, so that it can be positioned here, right? So that we can check to see whether or not any of these alpha particles are backscattered, scattered back into the direction from which they came, right? And Geiger went away and thought, good, this is something to give the undergraduate. This is a ridiculous experiment. We know all the particles are going right through the detector. Okay. But Martzen, all right, he was real happy. He gets to build this detector and swings it around and gets Geiger there to do the first experiment, puts the radium bromide, and they listen and they hear tick, 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 tick. Geiger says, oh, must just be background. Let me do a control experiment. Let me take the gold foil out of here. so that all the particles have to be going in this direction, all right? So they take the gold foil out of there, and they listen, and they hear nothing. They put the gold foil back, and they hear tick, 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 tick. And they put a platinum foil in there, and they hear tick, 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 tick. Whatever metal they put in there, hey, there were some particles coming off. And they got Rutherford down in the lab. And Rutherford looks over their shoulder. They do this again and again. Hey, it's real. It's real. And what's coming off? Well, the count rate is about 20 particles per minute. All right? Not large, but not zero. All right? And the probability here of this backscattering, right, is simply the number of particles backscattered, which is 20, over the total number of particles, or actually the count rate of the particles backscattered over the total incident count rate. So that's 2 times 10 to the minus 4. Hey, that's not 0. All right? So, wow. Rutherford was excited. Rutherford later wrote, "It was quite the most incredible event that has ever happened to me in my life." It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Okay, so what was the interpretation? The interpretation is, gee, the atoms, the gold atoms that make up this foil, hey, they must be mostly empty, right? Now, they knew that those atoms had some electrons in it because the electron had already been discovered. But these alpha particles seem to be going right through those gold atoms for the most part. So the atom, which he knew to be a diameter of about 10 to the minus 10 meters, hey, most of that atom must be empty, was the conclusion. But occasionally, these helium double plus ions, these alpha particles, occasionally they hit something massive. Right? And that something massive then scatters those helium ions into the direction from which they came. And since that probability is small, well, the size of this massive part, it has to be really pretty small. And from knowing the probabilities and knowing roughly what the diameter of the atoms were and how many layers of atoms he had, he was able to back out of those experiments a diameter for this massive part of 10 to the minus 14 meters. All right? And he called this massive part the nucleus. And he called it the nucleus in analogy to the nucleus of a living cell, the heavy part, the dense part in a living cell. That's where the name the nucleus comes from. All right, now, Rutherford also realized that this nucleus here has to be positively charged because he knew about electrons and he knew the atoms then were neutral. And so he reasoned this nucleus had to be positively charged. And then he did a bunch more experiments, more sophisticated experiments, in which he actually measured here the angular distribution of the helium ions scattered from the nucleus. And from those very detailed measurements of the angular distribution, he was able to back out the fact that this nucleus was, the charge on it was actually plus Z times E. So Z is the atomic number, E is the unit charge. He did a bunch of different metals. He was able to establish that that nucleus had a charge of plus Z times E. All right? So his model is that there's a very dense center, 10 to the minus 14 meters. This diameter of the nucleus is something that every MIT undergraduate should know. All right? And he realized that then the electrons have to fill out, the rest of this volume. All right? So that was his interpretation from these results. And think about Martin. What a great Europe experiment. He discovered the nucleus. Isn't that great? Martin had a long and successful career as a scientist also after that. All right? Now, should also tell you that this backscattering experiment is really the essence of how a quark was discovered. Quark are the fundamental elementary particles in protons and neutrons. And essentially, they took a high-energy particle, scattered it through the proton or the neutron, and it backscatters. And in that way, they discovered the quark and measured the diameter of the quark. And this was done by a couple of my colleagues in the physics department, Jerry Friedman and Henry Kendall, who has since passed away. But Jerry Friedman's still around, and I'm sure many of you, he loves to talk to undergraduates. Many of you will get that opportunity. All right, but now it's time for us to do our own Rutherford backscattering experiment. Okay. Okay. So here's our gold lattice. These styrofoam balls are the gold nuclei, right? The space around them are the electrons. These things in the center here are just the posts on this frame, right? This is a piece of equipment from my lab that I pressed into service, and so I couldn't cut these posts away because I would have trouble taking my manipulator out of my machine at a later time. So, they're just there. But this is our one monolayer of gold nuclei. And so what are we going to do? Well, what we're going to do, right, is we're going to try to measure the diameter of these styrofoam balls in the same way that Rutherford did. And so we're going to need some alpha particles, right? So what are we going to use for an alpha particle? Well, graduate students, well, we got some ping pong balls for alpha particles, all right? So let's do that. We've got alpha particles. We have 287 alpha particles, or ping pong balls. And we're going to measure the probability of backscattering. So the probability of backscattering will be the number that actually backscatter divided by the number that we throw at it, or the total number. Okay? So that's what we're going to measure. Okay, but now I have to take this probability and I have to relate it to the diameter of these nuclei. All right? So how am I going to do that? Well, that probability is going to be equal to the total surface area of the crystal here, right? The total area, and I've already measured that. I know that that total area is 2,148 square inches. So that's in the denominator, but now in the numerator is simply the total area of the nuclei. The total area of the nuclei is the area of one nucleus, A sub I, summed over the total number of nuclei, which I've already counted is 119. All right? And so the total area is 119 times the cross-sectional area here of any one of these nuclei. And that's pi d squared over 4. So I can solve that equation for the diameter in terms of the probability. And when I solve that equation, d is equal to 4.79 times the probability to the 1/2 power. Okay? All right. So what we're going to do is we're going to measure this probability, okay, by throwing the ping pong balls and calculating and determining how many backscatter. And then we're going to use that to get this diameter of the nuclei. All right? Same experiment that was done to actually measure the diameter of the nucleus. Okay, so now you're going to do this experiment. Every one of you are going to get a ping pong ball from the TAs. The TAs, why don't you give out the ping pong balls, and then I'll give you some instructions. Okay. All right. That's the the pi d squared over 4 is the cross-sectional area in terms of the diameter of these balls. Okay? Right? I just wrote it in terms of d instead of r. Okay? Okay. Yes?
Doesn't the fact that what we're shooting at the system has volume going to throw the calculations off? Like, you have to assume that it's close to a point size compared to...
That is correct. The balls, that's a good point. The balls that we're throwing actually have size compared to, in the case of the Rutherford backscattering experiment, where the projectile was almost a point compared to the size of the nucleus. In our experiment, you're quite right. Our balls are about the diameter there. And so if we were doing a more exact experiment, we'd do a little more different calculation. We'd take into consideration the size of the actual ball that we were throwing. But we're not going to do that. All right? It's because we're not throwing that many balls, right? We don't really have the statistics to do a more exacting kind of calculation. Okay? But you're quite right. Okay, yes?
Seeing as Rutherford didn't know at the time what the alpha particle was, how was he able to know whether he should take into account the relative size of the alpha particle?
Well, yeah, he didn't know, right? Although he knew the fact that it was backscattering, that it had to be much, much less massive than the nucleus. I think that he also measured the energy of the backscattered particle. And from that, you can back out the fact that it is much less massive than the nucleus. So there are a few other details, you're quite right, that I've left out in this discussion that he had to know in order to get this number. Okay? Okay, so here's the thing. You have to aim your alpha particles at this lattice, all right? And then you got to watch your ball. You have to watch to see if it scatters back at you, all right? Because at the end, I'm going to ask you if your ball backscattered, all right? And we need an accurate count, all right? Now, if you hit one of these things and it backscatters, that doesn't count, all right? Only if it hits the styrofoam ball does it count. If it hits the styrofoam ball and goes through, that doesn't count. So it really, literally has to backscatter at you. Okay? Was there a question over there?
Yeah, what if you miss?
If you miss, you miss. Okay, now, I do invite you to come a little closer so that you can at least hit the crystal. Right? Yes?
Isn't like the mass of an alpha particle less than the mass of like a cold nucleus, and this is kind of opposite, like it's a lot bigger than that?
That is correct. That is correct. Well, yours, you've got a defect. These are a little bit lighter. Oh, you got some more here. Oh, okay. Yeah, you can have a regular one. Anybody need one yet? I got a couple. Oh, all right. You need one? Because I need them all thrown. Okay, did you have a question?
What's the decay pathway for the radium bromide, and how does that make the alpha particles?
What is the mean free path?
Yeah, what's the decay pathway for the radium bromide? Like, what actually does it do to make that alpha particle?
That I'm going to have to give you an expression for it some other time, okay? But there is certainly a decay pathway, okay? Okay, I got another ball here. All right, now, are you ready? Okay, you can come down closer, but now I have one piece of advice for you, all right? And that is that only fools aim for their chemistry professor. Okay, so go to it. Did you throw your balls? You missed the crystal. All right. Has our supply of alpha particles been exhausted? All right, all done? All right. Hey. Now comes the big test. How many of you had an alpha particle that backscattered? Okay, you'll have to keep your hand high because I got to count accurately. Okay, in this section I see 1. You 2. Cheater. No. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Did I get everybody? Okay, I got everybody, 13?
Backscatter, not deflection.
Right, not deflection, right? If it hit and it went through, that doesn't count. It has to come back at you.
That's a function of how quickly it hurts the ball.
Yes.
Don't raise your hand.
That's right. Okay, all right. Does anybody want to change their count? 13 balls?
Will the nuclei ever move like that one?
I'm sorry?
Will the nuclei ever move?
If it just hit it and moved, but it didn't backscatter, it doesn't count.
But will the nuclei move?
The nuclei will move, yes. No, they will move, certainly, because there's a momentum transfer. Right. Well, not quite like that, no. Okay, we got 13 balls. That backscattered? Okay. So, let's see what we got. All right. The probability here then is 13 over 287. That probability is equal to 0.049. Okay? If I now take this probability and I plug it into here, all right, what we're going to get is a diameter of 1.0 inches, okay? And the diameter on the average of those particles is about 0.85 inches. All right, so you did a really pretty good job. You got the diameter of the nucleus. Okay, that's great. And that's the way the nuclear diameter was, in fact, measured, discovered. All right, but now we have the problem that the scientists had in 1912, and that is, what is the structure of the atom? We now know it has a nucleus, it has an electron. How do they hang together? Where are they in the atom? So we're going to talk about the classical description here of the atom. And the first question that we have to ask is, what is the force that keeps the electron and the nucleus together? So what are the 4 fundamental forces? What's the weak? Gravity, gravity's 1. And that is the strongest or the weakest? Weakest. All right, gravity. Next, stronger force? Electromagnetic. I'll just abbreviate it. EM. Next, stronger force. Weak force. And the next? Strong. All right. Weak and strong are intranuclear forces. They are operable between the protons, the neutrons, and the other elementary particles that make up the nucleus. It doesn't have a lot of effect, the weak and the strong force, on chemistry, except for beta emission for the radioactive elements. Gravity. Gravity actually does have no known chemical significance to chemistry. And so all of chemistry is tied up here in the electromagnetic force, which I am, at the moment, going to simplify and just call the Coulomb force. All right? All right. Now, we know how to describe the Coulomb force between charged particles. We know what expression to write down. Let's do that. So if we have the nucleus, it's positively charged, and the electron here, which is negatively charged, and they're at some distance r between each other, the expression that describes how that force of interaction changes with distance is Coulomb's Force Law. It's just the magnitude of the charge of the electron times the magnitude of the charge on the nucleus over 4 pi epsilon naught times r squared. I'm going to just treat the force as a scalar, just for simplicity purposes here. Epsilon naught is the permittivity of vacuum. It is a factor in there for unit conversion. R then is the distance between the electron and the nucleus. All right. So what does this say? Well, this says that R, when R goes to infinity, what is the force? 0. The particles are infinitely far apart. There's no force between them. In this case, an attractive force between them. When R is equal to 0, what is the force? Infinite. And anywhere in between, well, that force is described by this 1 over r squared dependence. So you can see that as the particles come closer and closer together, the force between them gets larger and larger. As the closer they get, the larger the force, the more they want to be together. Right? So this expression is just telling me if I held one particle and the other particle in my hand, and I held them at some distance between, held them some distance from each other, that expression is just telling me the force with which I have to kind of exert to keep them apart. All right? But now, if I let them go, well, you know what's going to happen. They're going to go, they're going to come together, or they're going to want to come together because of that force. And what is not in this expression, what is not in that expression is any information, time, right, is any information about how those particles move under influence of that force. Nowhere in this expression is there an r of t, how that distance changes with time. And so what we need to describe that is we need a force law. Hey, and in 1911, the force law that seemed to describe the motion of all bodies, including astronomical ones, is, of course, the equation of motion that described how bodies moved are Newton's equations of motion, and in particular, F is equal to ma. And of course, I can write that acceleration as a time derivative of the velocity, dv by dt. And that velocity, of course, itself is a change in the position with respect to time. So this is m, the second derivative of r, with respect to time. Okay, so if I know the force that is operating, which is this, I can take this and plug it in here, and I'm going to have a differential equation. And that differential equation is going to allow me to solve for what r is as a function of time, the distance between the two particles. And it's going to allow me to solve for that distance in a way that we call deterministic, exactly. In other words, if I know where the particles are to start with, using this equation of motion, this force law, I can tell you where those particles are going to be for all future time exactly. All right? It's deterministic, this classical mechanical approach. But now, in order to solve this equation, this differential equation, I'm going to have to develop a model for the atom. Right? All differential equations, for the most part, describing physical processes, are going to need something called, well, they're going to need a model. They're going to need some boundary conditions or initial conditions. And the model, of course, that came to mind for the atom is one in which the nucleus is in the center, and the electron moves around that nucleus with uniform circular motion and with a fixed radius. And we're going to call that fixed radius R star. All right? So, yeah, that's a planetary model. Hey, that seems like a good guess for the structure of the atom. All right, now, if you've got a particle undergoing uniform circular motion at some well-defined radius here, that particle is being constantly accelerated. And I can write that acceleration A as the linear velocity squared over that radius of its orbit. It's being accelerated because the velocity vector, right, the direction is changing, right? So there's constant acceleration. Now, this expression, for many of you, I've pulled out of the air. Some of you have seen it before. It's an 801 topic. You are going to see it this semester, but later on, okay, and in 801. So you're not responsible for this right now here, but you will recall, later on the semester that you've seen it here in 5 of 511 too. Okay, but if this is the acceleration, I can take this expression for the acceleration, plug it into here, plug in my force, my operating force law, right? And in so doing, I'm going to get, I'm running out of board here. Let me go over here. I'm going to get E squared over 4 pi epsilon naught R star squared. All right, that's the F. M times the mass times the acceleration, M times V squared over R star. Okay, so that's my equation of motion particular to this problem of a planetary model. And now I can solve that for V squared, the linear velocity of that electron going around the nucleus. And that comes out to be E squared over 4 pi epsilon naught M R star. Okay? Now, the reason I wanted to calculate the velocity squared here is because I want to calculate the kinetic energy. And that's easy to do. The kinetic energy, I'll call it K, is 1/2 M times V squared. So if I plug in the V squared right in there, I get 1/2 E squared over 4 pi epsilon naught R star. Okay? So far, everything looks okay. It looks okay. We got a planetary model. Coulomb Force Law is operable. We know the acceleration. We've just calculated the kinetic energy of this electron going around the nucleus. But what I want to do now is I want to know the total energy of the system. I just calculated the kinetic energy of the system. But I want to know the total energy of the system. And the total energy of the system, and I'm going to call this just capital E, total energy, is the kinetic energy plus the potential energy. And I want the total energy of the system for 2 reasons. One is I want to show you that the system is bound, that total energy is going to be negative, that it is lower than the total energy when the electron and the nucleus are separated, right? I want to show you that within this model, this classical model, the electron and the nucleus do look bound. All right? So to do that, I need to show you the total energy is negative. To do that, I need to calculate the potential energy. So that's what I want to do. And secondly, I want to get an expression for the total energy, because using that expression, I'm going to show you how this classical mechanics fails, how Newton's equations of motion won't work to describe this problem, okay? Now, I've run out of time. I will do that on Monday, but that's where we're going. All right, see you Monday.